Okay. Good evening, Doctor. I'm called Sozio Rico of Group SWML26. I've come here on purpose to explain the four models that I trained as you wanted us to submit them. Right. So the contents of this presentation one, we have the introduction, two, architecture, then the others, how the models learn, how they work, the optimizer, hyperparameters, results, conclusions, and acknowledgement. So the introduction, I developed the 4 deep learning models that detect Babesia parasites from the microscopy blood smear images. The dataset contains of 4 classes. We have Babesia red blood cells, Plasmodium, and leukocyte. The 4 models that I trained were the 4 models I trained. I used the following architectures below, which is 1, the EfficientNet B4, the ResNet 50, the Swine Transformer, and the RegNet Y03. So those architectures gave rise to models which I named them using the very architectures you're seeing there. So both models were trained using the transfer learning from the ImageNet. Then the objective of training all these models was to compare their performance and determine which model is best for the job. The architectures, as Aaron said, we have the EfficientNet B4, which uses compound scaling to balance. Of course, it has parameters, for example, the network depth, the network width, and also the image resolution, which is 380 by 380. It's built on different or multiple mobile inverted bottlenecks, convolution blocks, all of them following a hierarchy until what we form what we call a fully concrete layer, which will contain our 4 classes well predicted. So it's designed for high performance deep learning. Then the other architecture is I think I should have given a visualization of these architectures because all of them have layers, and for ResNet particularly it has 50 layers built on the shadow blocks, which uses keep connections to improve the gradient flow. It prevents vanishing gradient problem, and also it uses a resolution of 224 by 224. It's known for its robust feature extraction. Then the other architecture was the Swine Transformer. For it has a hierarchical vision transformer using the shifted window attention. Of course, it processes images as patches. Then the multi-stage feature extraction. It captures both the local and the global context efficiently. So therefore, it has also multiple layers. But for this, you see that it uses the layer norm, the MLFs blocks, then also the residual connections. Input images were 224 by 224. Then for the RegNet Y032, it had a structured CNN design via the network design specification optimization. It's built using the bottleneck residual blocks plus the squeeze and excitation. It also uses the stage-wise scaling of the width and the depth. Image resolution 224 by 224. So how these models learn? Both models are using course-supervised deep learning. So the learning process is that each model has a pipeline whereby we input in images in this pipeline. So the pipeline processes these images where the model will extract these features of particular images we have fed in our model. Then our model predicts the class probabilities. Remember, I said we have 4 classes here. We have Babesia, leukocyte, Plasmodium, and the other was Babesia. So the predictions are compared with the true labels. Then error calculated is the error calculated using the focal length. So here I used the focal length for calculating the error. Since I saw there was a lot of imbalance in my data set, I used actually the focal length. Not only the focal length, I also used the white random sampler. So this combined gave me this combined helped me to deal with the class imbalance. Then we had back propagation that computes the gradient. Then the weights updated iteratively during the training. Then how models work. For the efficient B4 architecture, its model works through, of course, in fact, all these models, they work through inputting images through, then images pass through different layers depending on the architecture. So the feature maps are extracted, particularly for the EfficientNet B4. It extracts the feature maps at multiple depths. As I told you, it has the network depth, the network width, and the image resolution. So the squeeze and excitation models emphasize important feature channels. Then a global average pooling aggregates features. Then finally, we form what we call the fully connected layer that predicts the four classes that we had. That is Babesia, leukocytes, plasmodium, and red blood cells. Then equally to the ResNet 50, these images also pass through the convolutional layers. As I told you, these architectures have multiple layers where images go through, depending, they go through all these layers until we form what we call a fully connected layer that gives us these classes that are already classified based on the image fed on the pipeline. Then for the swim transformer, it also works through splitting the image into the small patches. Actually, when you see all these architectures, it talks about inputting images, processing occurring, then of course output being given. That for our main of course our main problem is a predictive diagnosis. We want to give a prediction on what type of disease on what type of a disease is an animal suffering from based on the blood smear that has been fed in our pipeline. So basically, when you check of how these models work, all of them follow the same procedures, because we start from the image goes through processing where features are extracted. Then, of course, normalization, optimization, everything is done through the pipeline until we come up with what we call a predicted value, which helps us to make informed decisions. So that's how basically all these models work. Then for the optimizer, I used for this case what we call the Adam W optimizer, that is adaptive learning rate optimizer. Yeah, therefore I used it, of course, remember we're suffering a lot whereby our data set was lagging behind in class imbalances. So therefore we had to look for optimizers that will help us to minimize the loss function. Then of course also helps us, of course, to determine how much the model parameters should change after each batch. That's why you're seeing the advantages there are adaptive learning rates, the YDK regularization, then the improved convergence stability. So here, it helps us to update the weights automatically. Then also, the network can learn properly from it. So additional optimization techniques were the course annealing learning rate scheduler. Of course, it's a strategy to adjust the learning rate during training. You can either increase or reduce the learning rate based on what you want, but actually the main goal is maybe if you want the model to converge earlier, you can increase the learning rate. If you want the model to learn slowly by slowly, you can reduce the learning rate. Then we have mixed precision. Of course, these are techniques where computation where we can use here we can either use full precision or half precision. It helps us to reduce, of course, the GPU memory usage. Then it speeds up also our training. Then here we used what we call also a weighted random sampler for the class imbalance. For this case, I told you I used two of them, focal length and the weighted random sampler. Of course, it helps us in oversampling and undersampling, where we can oversample the minority class and undersample the majority class. So that leads us to hyperparameters that I used. So basically, for the Swine transformer and the RegNet Y03 pipeline, it had those parameters, the hyperparameters you're seeing above, the batch size, the epochs were 25 with the early stopping of that. That means if converging of model training converges early, we had the epochs of 5, and it would help us stop it instead of completing the whole epochs. Then the learning rates, we had that, and so on. Then for the hyperparameters of the EfficientNet B4 and the ResNet architectures pipeline, for them, I used one pipeline. Even for this, all of them had two of these had one pipeline, then this had one pipeline, but with different specifications based on the architecture. So here, for example, for the EfficientNet, for example, for the EfficientNet, it takes image resolution of 380 by 380. Then for the rest of the architectures, they were using the image resolution of 224 by 224. So below are the hyperparameters of the EfficientNet and the ResNet. As you're seeing, batch size was 8, epochs with 25 still, but with patience of 5. In the case of early convergence, it will stop. Then the YDK as follows. So the results of the Swine transformer on the right hand, I have the RegNet Y02 architecture. So all these models, as you're seeing, their test report is as follows: the precision and so on. Then also on the other hand, I have for the EfficientNet B4 and the ResNet B4, all the test reports. All of them have the evaluation metrics where we have the precision, recall, F1 support, and accuracy. So for the overall accuracy for the EfficientNet B4, it was 99%. Equally to the ResNet, it was also 99%. Then basically for the Swine transformer, it has 98%. Then for the on the other hand, the RegNet, it had 99%. So basically, these models outperformed the Swine transformer by 1% actually. Then for the conversion matrices of both these architectures, when we look at the EfficientNet B4 conversion matrix, this has given us most predictions lie along the diagonal, meaning that the model has performed a bit well, actually, because when you track for Babesia, it's only one that it misplaced, and it predicted it at the red blood cells. It correctly predicted the leukocyte. There's none that was being inputted in different classes. Then we have the plasmodium, whereby 4 of them, 5 actually, were not predicted correctly. Our model predicted 1 plasmodium cell as Babesia, then the other 4 plasmodium cells as red blood cells. Then equally to the red blood cells, we saw the model predicted 4 of them incorrectly, where it predicted 1 red blood cells as Babesia, then 3 as plasmodium. Equally on this side, for the ResNet, we saw our model we didn't predicted most of its predictions lie along the diagonal, meaning the model correctly classified most of these images. So for the ResNet 50, we had 118 Babesia cells. 4 of them were predicted incorrectly, where you saw here 3 of them were predicted as red blood cells, 1 as plasmodium, then the other, the leukocyte, was predicted well, 100%. Then for plasmodium, it 5 of them were incorrectly predicted, where they were misplaced as to be the red blood cells. Then when we checked at the red blood cells, 4 of them were incorrectly predicted, because it classified 1 as Babesia, then 3 as plasmodium. So equally, these matrices equally, when you check on the Swine transformer and the RegNet, you saw that for the SwineNet, the model performed poorly on Babesia, but not all that poorly, because 4 of them were not predicted correctly, and it predicted 1 as the leukocyte, 2 as the plasmodium, then 1 as the red blood cells. Then, of course, all these models actually performed well on leukocyte. They didn't make any 100%. They didn't make any mistake. Then for plasmodium, on the Swine transformer, it misplaced only 3, where it predicted it as red blood cells. Then the other red blood cells were 5 of them were predicted as Babesia, then 7 of them as plasmodium. So meaning, based on this metrics, evaluation metrics, all these models, the rest of the models outperformed the Swine transformer. So when we check on the RegNet Y03, actually, based on this evaluation metrics, it was the one that had the upper hand, because it actually did no mistake in Babesia. It predicted it correctly. The leukocyte was predicted 100%. Then for plasmodium, it actually misplaced 3 of them, where it predicted them as red blood cells. Then for red blood cells, 6 of them were incorrectly classified, 2 as Babesia, then 4 as plasmodium. So when you compare all these, I came up with this conclusion, whereby you saw the model insights, the RegNet Y032 architecture gave us a best model with the overall F1 score of 0.99 with 9 errors, as you saw in the confusion matrix, and Babesia record of 1. That is 100%. Leukocyte was easy to classify, because all the models were able to predict it 100%. Then plasmodium was a bit hard, where we saw the F1 score of 0.9 between 0.93 to 0.96. Mainly confused, because it was mainly confused with red blood cells. So I think maybe some refinements will be done in order to say that I achieve, actually, since I'm the one who trained all of them. I'll try to revise my pipeline and see that all these anomalies, all the noise is extracted, and achieve best of these models. Of course, the trends are like I told you that 3 architectures gave us very good models which outperformed the Swine transformer architecture. Yeah, so based with this conclusion, I can say this is the end of my presentation. I will go to check on with my group members to see that what have they built, and we try to sit down and make evaluations, refine, and get one best model and deploy. So thank you for listening.